Defining things is hard, okay? Is a hot dog a sandwich? Is cereal a soup? The world may never know. When it comes to defining life, it's not much easier. But at minimum, we're pretty sure that to get to where we are today, life needed to replicate. Every known cell, including all the cells in your body, came about through replication of a preceding cell. But cellular replication, way too complicated. When scientists talk about how the first forms of life replicated, they have to think simpler. Far simpler. Like at the molecular level. All living things have DNA and have to copy it in order to reproduce. Problem is, copying the DNA molecule is also difficult. Why start there? Let's go even simpler. Scientists figure that RNA is a better candidate for the first replicating molecule. RNA is also found in all of life and is likewise capable of storing the instructions needed to build things, and it's a bit simpler than DNA. So, in 1962, MIT professor Alexander Rich first put forth the RNA world hypothesis, that all of life we see in the world today started from RNA. A few years later, in the late 1960s, this other guy, Saul Spiegelman, demonstrated the powerful ability of RNA to self-replicate, with a lot of help. He tinkered with it for over 75 generations in the lab and produced a molecule that could be replicated 15 times faster than the original. Wow! Fast forwarding a bit, in 1989, these guys, Sidney Altman and Thomas Cech, won the Nobel Prize for demonstrating that RNA can also have enzymatic properties. In other words, RNA can not only store information, we knew that, but it can also turn into simple tools that life needs to do the living stuff. Like a recipe card that can double as a paper airplane, or a frying pan, whatever. RNA could do multiple things. This is amazing. This put more wind in the sails of the RNA world hypothesis. Then, in the 2000s, these papers claimed RNA could self-replicate with just a little bit of help. Again, contradiction in terms, but hey, let's not get too picky, we're only getting started. Even more recently, in these papers, they claimed RNAs evolving right before their very eyes. Everything was coming together for abiogenesis in the RNA world hypothesis. There's almost certainly nothing we're missing in the hype, and there's no serious problems that would bring the whole house of cards down. No siree. Was replication of the first life as easy as they say, or is there more to the story that's being left out? These prior videos reviewed some of the challenges for producing anything close to RNA from natural processes and keeping it from degrading. But for the sake of discussion, we'll just pretend that RNA was easy to make and not a fragile ice sculpture in a Saharan desert that it really is. There are still a large number of challenges in getting RNA to self-replicate. Let's start with Saul Spiegelman, the guy with the RNA that never skipped leg day. The fact that they were able to replicate at all was thanks to them using non-prebiotically relevant conditions. AKA, this proof of concept experiment cheated by stealing an entire working Xerox machine called Q-beta replicase from something that was already living. Well, is it true that they were able to evolve these RNAs to be replicated much more quickly, at least? Technically, yes, but only because the RNAs devolved. After 75 generations of RNA replication, the resulting RNA had lost 83% of the information that they started with. The result was called Spiegelman's monster. A cancerous parasitic RNA that is replicated quickly, doesn't contribute anything useful, and uses up all the resources. This short, useless RNA will outcompete and dominate other useful RNAs, ones that can form useful catalysts or tools, because shorter, simpler molecules will be replicated much faster. Stripped of the hype, all they proved was that a useful strand of RNA, when replicated blindly, favors getting shorter and shorter, spiraling toward uselessness and malignancy. Not the direction you want things to go if you're rooting for chemical evolution. A recent review of this work commented, "Today, Spiegelman's molecules would not be described as self-duplicating." Next up, the Nobel Prize-winning discovery of Sidney Altman and Thomas Cech demonstrated that RNA can indeed act as both the instructions for building molecular tools as well as the tool itself. There was just a bit of fine print though. It can either do one or the other at any given moment, not both. In order for RNA to be read as instructions or replicated, it has to be unfolded. But in order for it to be useful as a molecular tool, or have a function, it has to fold up into a shape where it can't be replicated. That's a very important thing to note as we continue. Not only that, but RNAs only perform certain functions in life, and by themselves could not run all of the things needed for even very simple life. Sort of like if you're trying to build a house, you could get some work done with just a hammer. But the moment you needed to cut a piece of wood or unscrew something, you'd kind of be out of luck. Especially since RNAs generally don't work as well for tasks that proteins do. RNAs are really good at some things, like a Fisher-Price baby's first tool set. It's great at entertaining a baby. But if you need to actually hammer a nail or saw a piece of wood, those tools are ill-suited for that kind of work. It's not that RNAs are bad at what they do, any more than play tools are bad for playing. You just wouldn't expect the same level of function for things that proteins do. What about the more recent experiments? These papers didn't need the protein enzyme that Spiegelman stole to replicate his RNAs. These guys used clever methods that were completely RNA-based instead. That's pretty cool. The fine print with these papers, though, is that they designed a complex RNA, they cut it in half, and then used a whole one to mush the two halves back together again. So they claim self-replication. It's kind of like buying a car, cutting it in half, and then using another car to push the two halves back together, and claiming, I invented a self-replicating car. These papers took a different route. They did seem to make progress by having a pre-built string of RNA and chopped up complementary pieces combined together, but there's a lot of limitations. The main scientist in most of these papers, Jack Szostak, was a total bro and listed 8 serious challenges with RNA replication in this review paper. Of course, he tries to downplay them, but let's take a look more closely. Number 1, regiospecificity. In other words, when the building blocks link up, they kind of get deformed, grabbing a foot instead of a hand, so to speak. Like a paperweight, super simple RNAs can be a bit wonky and still do a thing because their thing is pretty simple. If we want a more functional thing, these kinds of deformations would be less tolerated. Number 2, high melting point of long RNAs.
In order to be replicated, a single RNA strand has to have some friends to link up with to make a complementary strand. And then, importantly, the two strands have to let go of each other. Problem is, the two strands want to link back together again. This is called annealing. And the longer the chain, the more tightly the two sides of the RNA are going to hold on, even at temperatures that would boil water and destroy RNA. If you can't get them apart without destroying them, it's a dead end.
Number 3, fidelity of template copying. When a molecule is copied, there's a chance for an error to sneak in. Occasionally, this is fine, but too many errors lead to something called an error catastrophe, where the whole sweater comes irreparably unraveled and jumbled. Number 4, rate of template copying. Basically, RNA as a whole has an expiration date, like yogurt. After a short while, they degrade and are no longer RNA. Since there's this timer going, RNAs have to replicate rather swiftly or die. Time is a constant enemy. Number 5, reactivation. Basically the same thing as number 4, but the building blocks themselves also have their own expiration date. Again, time is not friendly to abiogenesis. Number 6, divalent metal ions. These are things that are supposed to help, but they actually degrade the RNA over time and hamper membranes too, especially magnesium. Number 7, primer-independent RNA replication. The mechanism these proto-RNAs needed to replicate required constant access to these primers, but the protocells would prevent this because the building blocks are too big. Number 8, strand re-annealing. In life, there are these enzymes that prevent individual strands of RNA that we want to copy from sticking right back together again, and it also keeps them apart. In proto-life, even if you could get RNAs to separate, they will just join up again before any substantial replication can get started. They have to remain separated if they're going to go on replicating. Spaghetti wants to stick. In number 9, something Szostak didn't mention, but it's an important problem: regulation. If RNA production isn't regulated, it'll lead to something we'll call the spaghetti conundrum. If nucleotides just naturally linked up to replicate RNA, all of a cell's stores of available nucleotides would rapidly be depleted. This would mean any protocell would just be full of a useless jumble of RNA spaghetti. Hang on, these papers show chemical evolution actually happening in the lab. They've literally shown changes in replicating RNAs over a number of generations that lead to better RNAs. So what about that? What they actually do is involve various forms of cheating to claim self-replication. These papers stole a relatively large RNA from existing life. And it already had an unusual ability. It had 4 parts that can come together to form a complete RNA. So they played with these pieces for a bit and rearranged some of them with fun new results. Interesting, but not self-replication or relevant to the origin of life at all. This one steals even more things from life, the entire translation system, hundreds of genes. Basically, they didn't just steal a Xerox machine, they stole the whole supply chain and factory. Okay, but haven't you heard of the RNA peptide world? It's gaining momentum with scientists these days. They say that RNA didn't act alone to start replication. Maybe RNA in these peptides or junior proteins helped each other replicate, like these papers suggest. Sure, peptides do make RNA more stable, increasing its shelf life, so to speak. But on the other hand, it gets in the way when it has to replicate. The RNA peptide world addresses almost none of the 9 problems we just raised with RNA world. They did produce some various peptides, but what they produced conveyed none of the information stored in the RNA, and there's no hint that this system would be capable of self-replication. That's not very promising for a protein manufacturing process. The RNA peptide world is gaining popularity, but notably, this work is an admission that the RNA world hypothesis is not well supported by actual evidence and is in need of serious help. Check out the title of this paper, The RNA World Hypothesis, the worst theory on the early evolution of life, except for all the others. Yeah, but hang on. This is just proof of concept, don't you get it? You're being too picky. No, yeah, I get it. If abiogenesis takes place over millions of years, it's unreasonable to make scientists wait that long to replicate it in the lab. We do need to use some shortcuts to make things happen within a reasonable timescale. That's fair enough. However, what's actually done is so far beyond that, and the results, even with this cheating, are so breathtakingly exaggerated that they bear little resemblance to reality. If we steal something from already living organisms in order to prove the concept that life could have started before that thing existed, that's not a proof of concept. That's clearly cheating. But that's just what these experiments do. There's an old story about a professor who was walking home and he fell into a deep pit.
I need to get a ladder to get out of this hole. Luckily, I've got a ladder at home. I'll just go get the ladder, bring it back so I can get out of this hole. A perfect plan!
The truth is, whenever you see a paper or popular article about the origin of life, you can pretty well bet that they're cheating in a number of different ways and that the headlines bear no relationship to reality. Importantly, these aren't problems merely because we don't yet know how these various processes work. The very concept of a self-replicating molecule that chemically evolves into life contradicts many very well understood laws and processes of chemistry, much like perpetual motion contradicts many well understood laws of physics. This isn't an argument from ignorance, but an objection from an abundance of data. When looking closer at the science behind the claims of prebiotic self-replication, it always involves human intelligence, scientists selecting, directing, and crucially, stealing components from already existing life. None of this work is proof of concept for the origin of life, no matter how loudly or frequently they claim it.